So the next talk is live pattern matching with typed holes, and we have Cyrus, Omar, who is going to present the work. And this is also a distinguished paper, so congratulations to the authors.
Way to tighten this, because I'm going to be typing. Yeah, like there was another session where they had a tool that they used. If not, I can be careful, but yeah, okay. Okay, hi everybody. So this is joint work with a number of co-authors. The lead author, Yongwei, actually did this work as an undergrad at Michigan, and he's now a PhD student at Purdue. Unfortunately, visa issues prevented him from coming to Splash this year, so I'll be presenting the talk today. So this is a paper about structural pattern matching, which is central to programming in functional languages, type functional languages in particular, but also increasingly features in many other languages. Our group is developing a type functional programming language together with a live programming environment called Hazel. So I want to start the talk just with a demo of pattern matching in Hazel. Let's hope the resolution cooperates here. Okay. So Hazel has data types like tree, so this is just an n-ary tree. It's defined in the usual ways, a leaf and a node constructor. This is a recursive sum type. And then you can write functions on trees, like this function that takes n-ary trees and converts them to binary trees by pattern matching on the input tree. So that's what case does. So what is pattern matching? It's just a way of doing a case analysis in a compositional way together with a destructuring binding construct for the product types that might appear. So you're matching in order on the tree, starting with this leaf n pattern where n stands for any integer n, and so on. So the node with the empty set of children, and so on, all the way up to 2 or more here. So this cons notation, if you haven't seen it, is just the head element x and the tail, y cons tail. So this is a really powerful way to write programs, of course. And in a type setting, you also have a really powerful set of analyses that you can do. You can do exhaustiveness checking and redundancy checking. So what is exhaustiveness checking? That just means that if I forget one of the cases that the type implies, then I will get either a warning or an error. In Hazel, it's an error. So if I delete that second case, I forgot the sort of the nullary node, then you get this error here, and it says at the bottom case expression is inexhaustive. You could actually show give an example of a missing case. We're working on that, but it's not currently implemented. So this is really powerful. Another analysis is redundancy checking. So redundancy checking comes up, for example, in subtle situations like this. So this example is the same as the last example, except I've reversed the order of all the rules. And because of that, the first rule actually subsumes the second rule, because this matches 2 or more elements in the list, whereas this matches only 2 elements. And so if I put my cursor here, it will tell me, hey, you might want to rethink this. This pattern is redundant. It will never be reached or never matched by anything that makes it to this point. So this is really powerful, but what Hazel's sort of claim to fame is that we support these kinds of analyses and execution during editing. So when the program is incomplete, and we use holes to handle this. So we have an editor that automatically inserts holes as necessary. We have expression holes, so I could go ahead and delete this, and it's replaced with this little hexagon, which is a hole. We even have type holes, so this is handled much the same way. So expression holes are modeled as contextual modal, as a sort of a metavariable and contextual modal type theory. Type holes are modeled as unknown types from gradual type theory. And this paper is about, well, pattern holes. So let me switch to another example here. So earlier in this development, perhaps we had a state that looked kind of like this. And so we had written maybe the 2 base cases here, and now we've sort of partly written this pattern here. So in Hazel, we really care about analyzing the exhaustiveness and redundancy properties of this code in a kind of refined way. And so here, what we're doing is we're saying, actually, there is no exhaustiveness error here. And it's not that this is an actually exhaustive set of patterns, right? I'm still missing several of the cases. What it is it's a possibly exhaustive set of patterns. So the way to think about that is a hole in a program is really sort of, it ranges over all possible future fillings of that program. Those are the possibilities that the program possesses. And so there is some way to fill this hole in this pattern such that this is exhaustive, right? I could fill it with the tail variable and it's exhaustive. There might be ways in which I could fill it in which it's not exhaustive. If I fill it with nil, then it's not exhaustive. And so we only give errors to users when it's necessarily inexhaustive, but as long as it's possibly exhaustive, then we don't give an error. A similar sort of reasoning will happen with this, except now we can give an error, an exhaustiveness error, even though there are still holes in the pattern. So it's not just that holes appear and therefore we don't do exhaustiveness checking. Here we can actually positively say there's no way to fill these two pattern holes such that this thing becomes exhaustive because this has necessarily two or more elements in it. And so we've missed the singleton case. Okay, so we give an exhaustiveness error here even though there are pattern holes in this program. Okay, so this is necessarily inexhaustive. So this binary exhaustiveness, inexhaustiveness distinction becomes a ternary distinction. Is it necessarily exhaustive, necessarily inexhaustive, or possibly exhaustive? A similar analysis can be done on redundancy. So here is a set of patterns that are exhaustive. And even though there's another pattern here at the end that has a hole in it, we know it's redundant with respect to the previous patterns because there's no way to fill it such that this wouldn't be redundant, right? Because essentially this pattern matches all lists that aren't nil. Okay, so a similar idea there. Let me actually go back and talk about the dynamic semantics really quick as well. So here I've written kind of an example of a call to binary with a node with 3 leaves, and I'm now calling a function with holes in it, and Hazel attempts to evaluate programs with holes. And so what does it give me? Well, it gives me an indeterminate result. It can't actually decide whether to take this branch or not, but it can decide at least not to take these first 2 branches. So it kind of crosses them out and leaves there sort of a pointer in this 3rd branch to say, I'm waiting for you to fill this hole to decide if this branch can be taken or not. Okay, so how does this all work? In the paper, we define Peanut. Peanut is a core calculus for pattern matching with holes. That's named after Hazelnut, which was the core calculus of Hazel. And so it's a fairly straightforward type lambda calculus. It's got base type of numbers, functions, products. We have explicit eliminators there for technical reasons. And then binary sums. Okay, so we just have the left and right injections there. And then we have, of course, pattern matching. So a pattern match expression has a scrutiny E and then a set of rules. It's actually a zipper of rules, so we have a pointer into which rule we're currently considering in the dynamic semantics. The patterns consist of variables, wildcards, number, literals, pairs, injections. And then in addition, in both expressions and types, we have holes, both empty holes standing for missing expressions, and non-empty holes standing for type errors that have been kind of wrapped in holes. We have a paper at Popple in January that talks about how all that works. So that's the syntax of the calculus. And we define an operational semantic. So I'll talk about the live evaluation aspect of it first. This is a pretty standard semantics for pattern matching. You start by evaluating the scrutiny to some final expression. It may not be a value because of holes, so we might be indeterminate. And then we have 3 cases. The case where the expression matches the pattern, in which case a substitution is produced and we step into that branch. If it doesn't match the pattern, then we move on to the next rule, which has to exist. And then there's this 3rd case, right? All these binary distinctions become ternary distinctions. So we have this possibly match or indeterminately match relation that creates a pause in the execution of that match expression. And so we have our standard type safety theorem. It's stated the same way as in the Hazelnut Live work. And so a few things to notice here. The context here requires an empty typing context in the standard way, but not a non-empty hole context delta, so you can evaluate programs with holes in them. And then another thing to notice here is that there's 3 possibilities for progress. It's either a value, indeterminate, or takes a step. There isn't the 4th one that you might expect of a match failure. So we actually don't allow match failure in type safety, which requires us to enforce exhaustiveness in the static semantics. So I'm not going to give all the typing rules. They're pretty standard. I'm just going to talk about the key ideas. So what do we do to do static reasoning about exhaustiveness and redundancy? Well, to simplify things, we abstract away from the actual syntax of the language into this syntax of constraints. This is a pretty straightforward mapping from patterns. So variable and wildcard patterns turn into a top constraint. Everything else has a corresponding constraint. Holes become an unknown constraint. And then we have a disjunction so that we can talk about an entire sequence of rules as the disjunction of the constraints from each rule. So we talk about entire sequences of rules at once in the constraint language. And then finally, we have an important operation, the dual or negation operation on constraints, which is something we can do by just adding a few more constructs, a bottom and a complement and an and. So for example, the complement of a left injection is either a right injection with a top or a left with a recursively complemented argument. Okay, so we'll see why this is useful later. Just want to introduce it there. So what do we do with constraints? Well, the most basic thing we can ask about a constraint is, does a given expression satisfy it? And again, we have these kind of ternary distinctions. So an expression could necessarily satisfy a constraint. It could indeterminately satisfy a constraint due to holes in either the constraint or the expression. And then the disjunction of those two we call possibly satisfying. So it's either necessarily or indeterminately satisfying. And we denote it with that question mark and the cross there. Okay, so how can we reason about exhaustiveness? So for example, this possibly exhaustive case from earlier. So the way to think about this is a rule, a sequence of rules will be possibly exhaustive if every expression possibly matches at least one pattern in that sequence. And so we can write that in terms of this, the satisfaction judgment. But you can also write it as an entailment. So entailment is a relation between two constraints, xi1 and xi2. And it just means that if every expression that satisfies xi1 must then satisfy xi2. And so you can write exhaustiveness as an entailment from top, right? Every expression must satisfy xi. Okay, so we've turned exhaustiveness checking into the question of entailments between constraints. Similarly, we can turn redundancy checking into the question of entailment between constraints. So for example, this necessarily redundant example from before, this one's a little more subtle, but it kind of makes sense. If you want to say that something's necessarily redundant, a pattern's necessarily redundant, then every expression that might match that pattern, possibly match that pattern, must necessarily match one of the previous patterns. That means it's redundant because you'd never reach it. It will necessarily match something before if it possibly matches P. So you can turn that into an entailment in the same way. There's a possibly and a necessary there. And so at the end, you get this kind of indeterminate entailment thing. So in yellow there, you see that the question of redundancy checking reduces to this question of an entailment between the constraints from the pattern you're considering as possibly redundant and all of the constraints previous to that pattern above it in the pattern match. Okay, so we've turned, in other words, these two questions into a constraint entailment question. And now how do we decide constraint entailment? So this is a little bit tricky because we have unknowns in these constraints. But we could eliminate these unknowns or these holes, okay? So there's a couple ways you might think to do that. One is you replace all the unknowns with a top. The other is you replace them all with a bottom. And it turns out that actually you have to use both of these at different points, okay? So the intuition here is that a constraint is possibly exhaustive if and only if you replace all the unknowns with top, and then it is exhaustive in the more standard sense. Okay, so that's just saying, like, put wildcards in all of the positions and you'll get exhaustiveness checking. Redundancy checking is a little more subtle. Because you're checking redundancy with respect to previous holes, you have to kind of like give the previous rules their most kind of conservative fillings with bottoms, and then you give the rule you're checking the top filling, and then together that entailment allows you to reason about redundancy, right? So you're saying like be pessimistic about everything coming before you, and then optimistic about the thing you're considering with respect to holes. Okay, so if we do that, then we get something without holes, and then we use some standard ideas that let me just remind you of. These come from kind of classical logic. So if you don't have unknowns, then you can turn entailments into just validity checks, or checks for tautologies in these constraints, which is just saying for every value a certain constraint is valid or tautological if that every value of the right type. So I'm kind of suppressing the type constraints here, satisfies that constraint. And then you can use material implication. So you might have remembered this from discrete math, right? So an entailment or an implication can turn into a not A or B, or in this case, not xi1 or xi2. And so you can turn this redundancy and exhaustiveness checking entailments into validity of material implication based hole-filled constraints. So you reduce the problem to this problem. And then finally, what can you do with checking validity? You can use the sort of dual again, so another not happens here. So you can say, well, a constraint is valid if and only if nothing satisfies its dual. And so at the end, you get these series of reductions from the original entailments down to these checks for duals, which you can actually decide using an inconsistency checker. Okay, so this incon judgment at the end. So you start with this, you move to validity, and then you move to an incon check. You have a couple of duals in here to make that work. And then finally, inconsistency checking can be stated algorithmically very straightforwardly. I won't go through all this, but it's basically just finding things that are next to each other that are inconsistent in this list of constraints. So in left and in right are inconsistent, numbers and their complements are inconsistent, things like that. So I went quick, I know, but all the details are in the paper. It's a very nice kind of logical formulation of pattern matching, not just for holes, although with holes. I think it's just like a very minimal logical explanation of pattern matching. There's a full set of metatheory. All of the theorems and implications and things have been mechanized in Agda. We also talk about scaling up to labeled sum types instead of binary sum types. And then there are some more sophisticated pattern matching systems where you want to use more sophisticated constraint solving. So there was a cool paper about adding constraint solving for pattern guards at ICFP 2020. So to support things like that, we also show a SAT encoding for this constraint solver, although you don't need it for just a simple checker. So I'll stop there. I just want to acknowledge that they're in the paper. The screenshots are from a previous version of Hazel 2. We gave the paper to a number of undergrads, and Andrew, my grad student, helped a bit. And they were able to read off the rules and turn them into an implementation for Hazel 3, which was a rewrite. And so I think this is a very practical system once you look at the rules. And I just want to acknowledge support from the NSF, and I'm happy to take questions.
Thanks for the great talk. So this seems like really interactive, right? I guess like you design the language well enough that like it can decide things like very fast. But in practical languages, like pattern matching usually has like side condition and stuff like that, and deciding whether or not like it's redundant or exhaustive might like take more time. Do you have like any concern about the usability when like things might time out or something like that?
We haven't encountered any programs large enough for this to be a performance bottleneck. I think the system that I mentioned by Graph et al. That would involve, of course, like calling into a SAT solver to decide if the Boolean pattern guards are mutually exhaustive. That would be hard to do on an every keystroke level. So in general, we have this problem in Hazel. So you could use various strategies. Run it in parallel and send the feedback later, and in the meantime you're sort of saying like it's indeterminately exhaustive because I haven't run the SAT solver yet, something like that. As we scale up, we'll hopefully encounter those problems and find solutions. Yeah.
Thanks for the talk. When I type in Hazel 1 plus whole, the result is 1 plus whole.
Yeah.
If I type 1 plus a case match where the pattern is not evaluated, is this going to turn into 1 plus that annotated case thing that you showed us with the patterns crossed out? So in other words, is this thing like a whole but with annotations?
Yes.
Okay, thanks.
Great. Thank you, Cyrus.